30 degrees below zero. Wind that kills an unprotected person in hours. No matches, no modern gear. For thousands of winters, Native Americans across the plains, subarctic, and woodlands didn't just endure this, they thrived. Not through one survival trick, but through a connected cold weather system of friction fire, engineered shelters, layered furs, stored food, and shared labor. Pull any single element, and the whole system could fail. Survival was never a single, uniform strategy. Across North America, distinct environments demanded highly localized knowledge systems, developed by sovereign nations over generations. The Lakota and Cheyenne on the wind-swept plains faced vastly different challenges than the Dene in the frozen subarctic forests. In the arid Great Basin, Shoshone-related communities adapted to cold desert winds, while eastern woodland families and Arctic Inuit engineered solutions for their own climates. A plains teepee, a subarctic brush structure, a Great Basin wickiup, and an Arctic snowhouse were not interchangeable designs, but precise physical responses to specific regional realities. Each of these diverse structures worked under the same laws of physics. Survival required managing metabolic heat, trapping still air, and keeping materials completely dry. A human body constantly radiates about 100 watts of heat, an energy source easily lost to frozen ground or biting wind. Preventing this loss required a connected system, protective clothing, dry fuel preparation, and reliable friction fire. None of these elements functioned in isolation. Together, they served a single purpose: to contain body heat and shape the immediate environment into a livable microclimate. A winter teepee used up to 20 brain-tanned bison hides, greased with fat to shed moisture. Inside, a second liner suspended 7 feet above the floor created a dead air cavity, raising interior temperatures by 20 degrees Fahrenheit. Adjustable smoke flaps regulated airflow, while snow banked around the exterior base sealed drafts. These lodges often featured east-facing entrances to catch the morning sun. In contrast, Mandan, Hidatsa, and Arikara families engineered massive earth lodges. The thick sod and timber roofs provided immense thermal mass, absorbing heat from a central hearth and slowly releasing it. In the interior Salish region, partially subterranean pit houses used geothermal insulation to buffer against extreme cold, while other forest communities built quick brush frame lean-tos insulated with bark, boughs, and moss. Where timber was scarce, compacted snow blocks became structural insulators. Because snow is 95% trapped air, it effectively halts heat transfer, allowing an igloo to remain 60 degrees warmer than the frozen air outside. The most immediate threat to a sleeping body is not the freezing air, but the earth. Sitting or sleeping directly on snow, frozen soil, or bare ground is a non-negotiable hazard, rapidly draining core warmth through conduction. To halt this heat loss, woodland and boreal families constructed thick mattresses of fresh spruce or fir boughs. While some historic accounts describe bough beds 12 inches or deeper, actual thickness varied by region and resource availability. This dense weave of evergreen branches trapped a layer of still air, isolating the body from the frost below. For overnight warmth, dense fire-heated rocks, wrapped in protective leather to prevent burns, were tucked safely into the bedding, radiating low, steady heat until dawn. Outside the shelter, personal survival depended on a mobile microclimate. Tailored garments functioned as high-performance gear, designed by skilled hide workers who understood thermal dynamics. For maximum insulation, subarctic travelers wore caribou skins or woven rabbit skin robes, which trapped dead air within hollow fiber furs. On the windswept plains, heavy winter bison robes provided thick, dense barriers against freezing gales. This clothing operated as a dual-layer system. A durable, windproof outer hide protected the inner insulating fur. To prevent sweat from freezing during physical exertion, travelers adjusted their layers, opening collars or loosening ties to regulate body heat during travel. Sweat is a silent, dangerous hazard during winter travel. Physical exertion produces perspiration, which quickly saturates clothing fibers and collapses insulating air pockets. When movement stops, this trapped moisture rapidly conducts warmth away, threatening to extinguish the body's internal fire. Protecting the feet required oversized moccasins packed with dry grass, moss, or fur, which absorb dampness while preserving insulation. For stationary tasks, people placed portable barriers, including thick firs, evergreen boughs, or wrapped warm stones, directly between themselves and the frozen ground. This focus on dryness preserved the core warmth and dexterity needed to ignite the next fire. At sub-zero temperatures, fire is the ultimate lifeline within the winter survival system. It dries saturated gear, cooks high-fat food, melts snow, and provides the warmth and morale needed to survive. Yet, igniting a friction fire in freezing, damp conditions leaves a razor-thin margin for success. In the plains and Great Basin, people use the hand drill, twirling a straight spindle, often cottonwood or yucca, between their palms against a notched fireboard. This method demands immense physical stamina, as the firemaker must maintain downward pressure and continuous rotation to grind wood fibers into a hot, charcoal dust. To gain a mechanical advantage in colder, more humid zones, subarctic and northern forest groups use the Buell drill. This system utilizes a bow, cord, spindle, fireboard, and handhold socket. By wrapping the cord around the spindle and applying steady downward body weight on the handhold, the operator saws the bow back and forth. This action multiplies rotational speed, generating an ember with less hand movement and strain. Choosing the correct wood was a matter of life and death. Firemakers paired dry, non-resinous species like cedar, willow, yucca, or cottonwood, while Arctic communities utilized driftwood. Once a glowing coal formed, it was transferred to a protected tinder bundle of frayed bark, dry grass, wood rot fungus, or cattail down, kept bone dry in sealed bark bags to shield it from the surrounding frost. Protecting this fragile spark during the transfer is a battle against ambient moisture. Throughout the ignition process, the fireboard, tinder, and emerging ember must remain raised off the damp snow on a platform of dry bark or flat split wood. The V-shaped notch in the board has already done its job, collecting the fine, dark wood dust and trapping friction-induced heat until the black powder ignited. Now, the firemaker carefully cradles the glowing coal inside the waiting tinder bundle, wrapping it loosely and blowing gently to introduce oxygen, nursing the heat into a viable flame. Once established, this flame is kept remarkably small to conserve scarce winter fuel. Placing dense, dry stones around the hearth protects the fuel from melting snow while absorbing thermal energy, which then radiates outward long after the flames die down. To avoid the constant, exhausting labor of gathering firewood in heavy drifts, firekeepers bank hot coals under a thick layer of ash or dirt at bedtime, preserving the embers for quick morning revival. Friction fire remained a highly valued, reliable method across the continent, with regional groups maintaining distinct variations suited to their environments. Generating metabolic heat in sub-zero cold requires high-fat fuel. Indigenous travelers prioritized fat to maintain core body temperature during winter journeys, drawing on highly concentrated energy sources. On the plains and in the boreal forests, this food system centered on pemmican, a name originating from the Cree word pimikin, meaning fat or grease. During the autumn harvest, specialized processors dried lean game or fish, ground it into powder, and mixed it with rendered tallow and dried berries. Eliminating moisture preserved the mixture for years in rawhide envelopes, yielding thousands of calories per pound. Across different regions, families secured these rations alongside smoked fish, wild rice, and cached roots in underground pits lined with bark to prevent dampness. These winter stores provided a stable foundation, supplemented by active cold weather hunting. Conserving the energy gained from winter food required mastering movement. Across heavy drifts of the subarctic, Athabascan travelers used wooden-framed snowshoes laced with tight rawhide webbing. This engineering distributed body weight across a wider surface area, preventing exhausting sinkage. Mobility, however, was as much about information as equipment. Hunters read wind directions, cloud patterns, and snow texture to anticipate storms, while following animal tracks and river corridors to identify safe routes. Travel timing and camp placement responded directly to the environment, using river valleys, tree lines, and sheltered terrain for natural windbreaks and immediate fuel, ensuring no movement or calorie was wasted. No single individual carried the weight of winter survival alone. It required a highly coordinated social infrastructure. Communities distributed essential roles across a network of specialized shelter builders, fuel gatherers, food processors, scouts, childcare providers, and weather monitors. Larger multifamily structures housed shared resources, preserving collective warmth while centralizing essential environmental information. At this group level, survival operated under a strict weak link principle. A single vulnerability, a poorly insulated shelter, damp tinder, insufficient fuel, an incorrect travel route, or depleted food reserves compromised the safety of the entire camp. Coordinated labor provided the necessary redundancy to buffer against these hazards, proving that structured community organization was itself a highly advanced, life-saving technology. Today, these ancestral systems remind us that survival is about aligning with nature through precise ecological engineering. These timeless principles of heat management remain the bedrock of modern outdoor design. Please like, subscribe, and comment below with what skills we should cover next.